Today we're going to be looking at how we can use calculus to solve some optimization problems. We're going to spend 2 days at least on optimization problems, but they'll be broken up over some other lessons as well. We want to start by looking at some of the classic optimization problems that you've already learned how to solve, and we want to see how we can take calculus and apply it to solving these problems. So the real classic optimization problem is the one that you see before you. A farmer has 800 meters of fencing, wants to enclose a rectangular field. One side of the field is against a highway that already has fence, so we don't need to worry about fencing that side. If this farmer wants to enclose the maximum possible area, what are the dimensions of this field? So let's start by just drawing a diagram to show what this looks like. Let's use the red line to represent our highway. We'll fence in this field. Since we have the highway on one side, we only need to use 3 sides of a rectangle to fence in this field. So we're interested in maximizing the area of that enclosed area. Call that side our length. The other 2 sides our width. So the perimeter of this field, given the fence that we need to use, would be equal to 1 length plus 2 widths. This is how much fence we've used. Or our 800 meters of fence has to represent 1 length and 2 widths. If we want to enclose the maximum possible area, well, our area of this field is length times width. So when you solved this problem in previous years, you would solve for one of our variables, L or W, and take that and sub it into our area equation. And then in previous years you would have distributed this and then use some completing the square to try and find the maximum, the vertex. We don't want to do that anymore. So instead, I'm going to distribute. So 800 W minus 2W squared. And then, remember from yesterday, we can use the derivative to help us find the max or min values. So if I find the derivative of area, my equation becomes 800 minus 4W and if I think about this area equation before I took the derivative, it would be like an upside down parabola. And that vertex, where my slope is 0, would be my maximum point. So if I set the area equation equal to 0, and then rearrange and solve for W, I get a width of 200. If my width is 200, then my length has to be 400. And now, without completing the square or graphing or anything, just by using calculus and the derivative, I've found the dimensions that give me the maximum area. The dimensions are by 200. Here's another classic problem that you've solved in the past, I think most likely in grade 9. Questions of this type: find two positive numbers whose, in this case, product is 10,000 and whose sum is a minimum. So we would let x represent the first number. We would let y represent the second number. And then we'd have two equations that we could set up and solve. X times y, the two numbers multiplied together, equals 10,000. The sum of these two numbers is what we're trying to minimize. And whenever you see the words minimum or maximum, you should be thinking derivative. We want to find the derivative of the equation for sum. Just like in the previous example, we want to do that by eliminating one variable. So if I took 10,000 and divided it by x, if I rearrange this equation, I would have an equation for y. So my sum equation can become x plus 10,000 divided by x, or x plus 10,000 times x to the power of negative 1. I can then find the derivative of the sum equation. And now this is the equation I want to solve. I want to find the minimum of this derivative by setting the derivative equal to 0 and solving for x. So rearranging, I would have negative 1 equals negative 10,000 times x to the power of negative 2, or clearing those negatives, I would have 1 equals 10,000 divided by x squared. Cross multiplying, x squared equals 10,000, which means that the square root of 10,000 would equal x. Remember, when you take the square root of both sides of an equation, you need to include these plus or minuses in front of the square root. So x would be plus or minus 100. Let's look back at the question. The question is asking us to find two positive numbers. So since we want positive numbers, we'll discount negative 100 as a solution. So if positive 100 is one answer, we can sub that into our equation for y to find the second answer. And then we can say that the two numbers are 100 and 100. When I multiply these two numbers together, my answer is 10,000. When I add these two numbers, I get 200, which is the minimum possible sum when we're looking at all possible factors of 10,000. Okay, and that's all I want to do for this video. In class tomorrow, I'm going to open up with this example that you can see on your screen. what I'd like you to do is try this beforehand. If I can give one clue as to how to start this problem, the 2,700 meters squared of material for this open top box refers to a surface area. So you need to consider this open top box so I have surfaces, I have a square base, and this box is of some height. Find the surface area of the open top box as your first equation. Use the volume of the open top box as your second equation and see if you can find the largest possible volume of this box given this amount of material. Okay, I'll do this question first tomorrow and then give you some time to practice some other optimization problems.